Hey guys, welcome back to my YouTube channel. So in this lecture, we are going to continue our discussion as we discussed in last class where we see about diode resistance. So today we are going to see about diode capacitance. So let me explain with the graph diagram. So let's take a scenario where we are reverse bias. So where in the reverse bias condition only depletion capacitance will act. So this is simple separation. So this is depletion region separation. Okay. So if we take the thing here. So because of these things, there will be some capacitance effect will act between these two. Here will be some capacitance acting. Okay, so this is how we will be taking. So this is only when it is reverse biased. So only in reverse bias condition, depletion capacitance will act. In forward bias, diffusion capacitance will come into picture. So let's now see about the first one, which is depletion capacitance. So depletion capacitance can also be named as transition capacitance or junction capacitance. Okay, so when the reverse bias voltage condition to the PN junction is varied, the effective capacitance will increase. So this is what the normal capacitance formula that we guys know, which the unit is farad. So we know the W, the depletion width, we have already calculated in one of the previous lecture. So from which, if we note it, the value will be 2 epsilon V naught plus modulus of VR. This I already said. Based upon the forward or reverse bias, the potential will be very here. So 1 divided by NA plus 1 divided by ND. Okay, so if we substitute that there, so we will be able to get that one. So when we substitute W in the W in equation CT, so if we substitute the W in equation CT, we will be getting some approximate term. So when we remove all the constant terms, and we will be able to get this required equation. So if we substitute and remove all the constant and name that constant as CT naught, then we will be able to get this value 1 divided by, which is the V naught power 1 by 2, okay, which is farad. The CT naught, which is nothing but, which is equal to root epsilon q divided by root 2 1 divided by Na plus 1 divided by Nd V naught. Okay, so this is the constant. I hope you guys able to understand this, right? So this is CT naught, this is CT naught. So which is one of the very important equation for the transition capacitance that is coming into picture. So from this we can generalize the thing. So it will be 1 by 2 if it is an normal uniformly doped. So the thing will be 1 by 3 if it is linear junction or non-uniform doping profile that I already discussed in the previous lecture. So this is because of the reverse bias thing. So we guys may wonder what will happen if the forward bias is coming to picture. So if the thing when it is connected to the forward bias, there will be another one type of capacitance that will act, that is diffusion capacitance, which is CD, right? So because of this thing, the forward bias, some kind of change in capacitance will act between the charge carriers, that is named as tau I divided by eta Vt. I is diode current, tau is the lifetime of magnetic charge carrier, and Vt is terminal voltage that you guys already know. So this is what the equation for the thing. So let me take a graph. So in which area what kind of capacitance will come into picture. So this is the thing. Here this is voltage equation V. So this is the cutoff voltage V naught. Okay, so this is voltage 0, this is 0 plus, which is 0 minus. So in this region there will be transition capacitance or depletion capacitance will act. So above the V naught there will be diffusion capacitance will act. But in this region between the 0 plus to V naught, both the CT plus CD will act. So both the capacitance will act. So this graph is very important. So when and what voltage level, what capacitance will act. So that we have to name it. So let me draw one high level approximation diagram here. So this is normal diode, right? So we may think normal diode, it will conduct the current when reverse bias, which will off when there is which will conduct the current when forward bias, and which will off when reverse bias. But that is not the case. There is many approximation that we have to take into picture when we are analyzing the diode. As an engineer, we have to do this. So this is low frequency analysis. Here it is high frequency analysis. Okay, so how the things can be modeled is that, let me draw perfectly. So in high frequency, the diode will be, whatever thing will come into picture is the diode resistance. In DC also, the diode resistance will come into picture. So which can be named as RD, and here also it can be named as RD. Okay, both are same. So here two kind of capacitance will act in a higher voltage. So which is CT as well as CD. So both kind of capacitance will act in the higher frequencies. So which is P terminal, which is N terminal. So here only RD will act at the low frequency P to N. So only at the low frequencies we will be taking care of only resistance. But in case of high frequency analysis, we need to take care of both RD and both the kind of capacitance that need to be taken care. So these are some kind of prerequisite that we need to take into picture while analyzing the diode. So as we discussed in the last class, right? So resistance, because the slope can be, from the slope we can calculate the resistance. But in the capacitance, we cannot calculate the capacitance from the VI curve or any kind of curves. So in most of the case, if they ask something on the application or something to calculate, then they will be providing the constant or capacitance value to us. So from where we can calculate the capacitance and then we can model the diode. So the diode modeling, those things we will be seeing in the analog device circuits. That is another one different course. So here only fundamental mathematical behind the theories. But in analog devices, we'll be completely focusing on problematic and those kind of things. So where we'll be seeing about diode modeling. We have 3 to 4 types of diode modeling. So there we can analyze all the things. So for now, this will be fine in the EDC or semiconductor physics subject. So in next class, let's start about Zener diode. So I hope up to this you guys able to catch it. So if you guys have any doubt, please ping in the comment section. I will clear it. So thank you. Stay tuned for next lectures.